Right now, the strongest force on you isn't gravity pulling you down, it's the floor pushing you up. That sounds like I'm playing word games. It isn't a trick. It's the first step to understanding gravity in a way most classes never bother to teach, because it forces you to separate two things we casually mash together: what gravity does and what you feel. Do this with me for 10 seconds. Stand up if you can. Don't jump. Don't move. Just stand there. You feel your weight. It feels steady. It feels like gravity is doing something to you continuously. Now here's the weird part. In that moment, you are not accelerating. Your speed isn't changing. And in physics, no change in speed means no net force. That's Newton's first law. So either Newton is wrong, or your story about what your weight is wrong. What are you actually feeling? You're feeling the ground pushing on your feet. If you had a bathroom scale under you, the scale would push back with exactly the amount needed to keep you from falling through the floor. That push is what your body interprets as weight. It's a contact force. It's a shove. If the floor suddenly disappeared, gravity would still be there, but that push would vanish, and the sensation you call weight would vanish too. So let's say it cleanly. Your weight is not the force of gravity. Your weight is the force required to prevent you from freely falling. Once you say it that way, a lot of famous mysteries become strangely simple. Why do astronauts feel weightless in orbit? People say because there's no gravity in space. But that's not true. Gravity is absolutely there. The reason they float is that nothing is pushing on them the way the ground pushes on you. They're in free fall. The whole spacecraft is falling. They're falling at the same rate, so relative to the ship they just float. And if that sentence feels uncomfortable, if you're too hinking, but they're not falling down, they're going around, good. That discomfort is the doorway, because orbit is just a very special kind of falling. Here's a thought experiment that Feynman would love because it uses almost no fancy words and it corners you with your own intuition. Imagine you're in an elevator, a normal elevator, and you're holding a spring scale, a little force gauge. You hook it to a small weight. When the elevator is sitting still, the scale reads some value. That's the pull the spring feels, which is really the weight pulling on it and the spring pulling back. Now the elevator starts going up. You feel heavier for a moment. The scale reading increases. Your body feels extra pressed into the floor. When the elevator slows to a stop at the top, you feel lighter for a moment. The scale reading drops. Why? Did gravity change? No. Gravity didn't care about your building. What changed was acceleration, whether the floor was pushing you a little harder or a little less hard than usual. Now imagine the elevator cable snaps. This is the moment teachers often skip because it's morbid, but it's the cleanest piece of logic you'll ever see about gravity. When the cable snaps, the elevator and everything inside it begin to fall together. What does the scale read? It reads 0. Not because gravity disappeared. Gravity is the reason you're falling. It reads 0 because the spring has nothing to pull against. The weight and the scale are both accelerating together. There's no stretching of the spring, no contact force, no felt weight. That's why astronauts float. They're in an elevator with a very long drop. So if you want the honest story, start with a bathroom scale, because that scale does not measure gravity. It measures how badly something is trying to stop you from doing what gravity would otherwise make you do. Follow your free fall path. Now you might be thinking, okay, fine, weight is a push, but gravity still pulls. What is that pull? Good. Now we can talk about gravity itself without mixing it up with the sensation of weight. The simplest description we have, historically and mathematically, is Newton's, and it's almost insulting how well it works. Newton says every mass attracts every other mass with a force that depends on two things: how massive they are and how far apart they are. Double the mass, double the force. Double the distance, the force drops by a factor of 4. That inverse square drop is not a random preference, it's the geometry of space. The influence spreads out in all directions, and the area of a sphere grows like distance squared, so whatever effect you have gets diluted by that area. Newton's rule is so accurate that if you use it carefully, you can predict the motion of planets, the trajectories of comets, the fall of apples, and the way a cannonball arcs through the air, at least until air resistance and Earth's rotation start to matter. But Newton's rule also contains a philosophical itch. It says gravity acts at a distance. The Earth pulls on the moon across empty space. No rope, no jet, no contact, just pull. You can use the rule to calculate what happens, but it doesn't tell you what's in between. What's doing the pulling? How does the Earth even know the moon is there? If the moon moved, how long would it take for gravity to change? Newton's math doesn't naturally answer that. Feynman's attitude toward this is refreshing. Don't pretend you've answered a question you haven't answered. If you have a law that predicts, celebrate that. If you don't know the mechanism, admit it. Confusing "we can predict" with "we understand why" is how you end up with fake explanations. So Newton gave us a rule so accurate it can steer spacecraft, but it answers a different question than what is gravity. Because Newton's law is like a perfect accounting system. It tells you the totals. It doesn't show you the machinery behind the curtain. And here's where the story turns. The deeper explanation that your teacher likely never gave you is not Newton was wrong. Newton is unbelievably right within its territory. The deeper explanation is that Newton's force picture is not the most fundamental way to describe what's happening. It's a powerful translation of something more geometric. To feel why, we go back to your own experience. Picture a ball thrown sideways, not straight up, not straight down, sideways. If there were no gravity and no air, the ball would move in a straight line forever at constant speed. That's Newton's first law. Straight line motion is what happens when nothing interferes. But with gravity, the ball curves downward. It accelerates downward while continuing forward. You get a parabola in the ideal case. Now increase the forward speed. Throw it faster and faster. It goes farther before it hits the ground because it spends more time moving sideways while gravity pulls it down. If you throw it fast enough, something incredible happens. The Earth curves away beneath it at the same rate that the ball falls. The ball never hits the ground. It keeps falling and missing. That is orbit, a perpetual miss. So when you imagine the moon going around, you should imagine it as constantly falling toward Earth and constantly missing Earth because it has sideways speed. This is why the no gravity in space story is such a mess. The moon is held in orbit by gravity. It's falling all the time. It is in free fall. That's why if you were standing on the moon as it orbited, ignoring practical details, you wouldn't feel a downward push from some orbit force. You'd be floating in the local sense. You'd feel weight because the moon's surface pushes on you, but the orbital motion itself is free fall. Now here's the clue Einstein couldn't ignore. Gravity doesn't care what you're made of. This is one of those facts that is so ordinary it becomes invisible. Drop a rock and a wooden block. Ignoring air resistance, they fall together. Not roughly together. They fall at the same rate. If gravity were like electricity, different materials would respond differently. Some objects would be more gravitational in the way some materials can be charged. If gravity were a drag, it would depend on shape and composition. But in vacuum, everything falls the same. That universality is shocking. It's the reason Galileo's Tower of Pisa story is even a story. It's the reason you can do physics with simple objects and trust that the result isn't an accident of your material choice. In Newton's framework, you can fit that into the math by saying gravitational mass and inertial mass are proportional, and experimentally they're equal to a ridiculous precision. That's a statement about nature. The thing that determines how strongly you respond to forces is the same thing that determines how strongly you gravitationally attract and are attracted. Einstein stared at that and saw something that isn't obvious at first. If all objects fall the same way, then free fall is not like being pushed by a normal force. A push usually depends on what you're made of. A rocket engine depends on mass. A magnetic field depends on charge. But gravity seems to be indifferent. So he asked a wicked question. What if free fall motion is the natural straight line motion, and what we call a gravitational force is what we invent when we insist on describing motion using the wrong kind of straight line? That sounds abstract. So let's make it concrete with something you've experienced without noticing. Consider flying. If you look at a map, you might think the straightest route from one city to another is a straight line on the paper. But pilots don't fly straight lines on the map. On a flat map, the shortest route from New York to London often looks like an arc bending north. Why? Because the Earth is curved. The shortest path on a sphere is a great circle, and when you project a sphere onto a flat map, those shortest paths look curved. Here's the key. The plane isn't being pulled north by a mysterious force. It's following the straightest possible path on the curved surface. The path looks curved only because you are using the wrong geometry to judge straightness. Einstein's move was almost insulting in its simplicity. He stopped treating falling as something happening to you and treated it as what you do when nothing is touching you. In his picture, space-time itself has geometry. Matter and energy affect that geometry, and objects moving freely, no engines, no pushes, no contact forces, follow the straightest paths in that geometry. Those paths are called geodesics, but you don't need the word. Think great circles, but in space-time rather than on Earth's surface. Now notice how beautifully this matches the elevator experiment. In the snapped cable elevator, you feel weightless. In Einstein's logic, that is the hallmark of free motion. You are moving straight through space-time. You only feel weight when something prevents you from following that natural path, like the floor holding you up. Standing on Earth is, in this view, not inertial motion. It is accelerated motion. Your feet are literally being pushed upward by the ground, preventing you from taking the free-fall path you'd otherwise follow. This is why the opening sentence is not a trick. When you stand on the ground, gravity is not the force you feel. The force you feel is the ground fighting your tendency to fall alone. Geodesic. So the simplest honest statement is, in free fall there is no gravity force in your local frame. Gravity shows up when you compare nearby free fall paths and see them converge or diverge. It shows up as tides, differences in gravitational pull over distance. It shows up globally as curvature. That's also why the rubber sheet analogy is both helpful and dangerous. It gives you a picture of curved space, but it smuggles in an external gravity pulling balls down into the sheet, which is exactly what you're trying to explain. It's like explaining sleep by showing someone a painting of someone sleeping. It's not wrong as a metaphor, but it can confuse mechanism with illustration. A better way is to keep asking, what does a freely falling object do? It does the simplest thing it can do. It follows the straightest path available in the geometry it lives in. Now, if this is true, something else must also be true, whether you like it or not. Once gravity is geometry, it can't just bend paths. It has to reshape time itself. This is where people often get lost, because time feels like something universal and untouchable. But in physics, time is what clocks measure. And clocks are physical systems. Atoms vibrating, springs oscillating, electrons flipping states. If space-time geometry changes what counts as a straight path, it changes what counts as the same amount of time along different paths. There's a simple way to say it without drowning in equations. In Einstein's picture, gravity is not just an acceleration field. It is a structure of space-time, and the structure of space-time determines how clocks tick. Near a massive body, the geometry is such that the time coordinate you'd use far away doesn't match the proper time along a clock's path close in. When people say gravity slows clocks, they're compressing a geometric statement into a sentence. It's not that gravity is a sticky substance that gums up time. It's that different world lines through curved space-time have different lengths, and clock time is the length along your world line. If that sounded like a mouthful, you can still hold on to the practical anchor. If gravity affects the geometry and time is part of that geometry, then time can't stay untouched. That's not an extra feature. It's part of the same structure. And if you ever wonder why physicists take this seriously, it's because it isn't just philosophy. The predictions are testable. Clocks at different gravitational potentials tick differently. The effect is small in everyday life, but real. The universe is stingy with surprises, and when you find one that repeats reliably, you build theory around it. Now we've climbed from your feet on the floor to space-time geometry, but we still haven't paid off the title completely. The title promises a way of explaining gravity that your teacher never gave you, and the real payoff is a synthesis that makes gravity feel less like a mysterious downward pull and more like a consistent story that matches every experience you've ever had. So let's put all the pieces together and see what gravity looks like when you stop mixing up sensations, forces, and geometry. So the punchline your teacher skipped is this. In the deepest sense we currently have, gravity is what the universe looks like when straight isn't what you thought it was. When you stand still on the ground, you are not doing nothing in the relativistic sense. You are being accelerated upward by the floor. You feel that acceleration as weight. That's why the scale reads something. That's why your knees compress. That's why your muscles work even when you're just standing. Your body is fighting to keep you off the natural freefall path. When you jump, you briefly stop feeling the push. In that instant between leaving the ground and landing, you are closer to the natural motion. You are in free fall. You are locally weightless. The only reason you don't notice it is that the time is short and your brain is busy with other things like not falling on your face. In orbit, the time is long. The whole environment is in free fall together. That's why you float, not because gravity turned off, but because the push turned off. Newton's gravity is what you get if you choose to describe all of this using a flat absolute space and an absolute time, and then you force the equations to match the observed accelerations. You end up inventing a force field that points toward masses and falls off with distance. It's a brilliant compression. It works incredibly well in weak fields and low speeds. It's what you'd use to build bridges and launch satellites in many cases. Einstein's gravity is what you get when you notice that free fall feels like inertia, that all objects share that motion regardless of composition, and that the deepest way to express that is free motion is straight motion in a geometry that matter shapes. Gravity is not a push. It's what's left when you let go. And then the story becomes coherent in a way that the usual classroom version often fails to deliver, because the classroom version tends to say, gravity pulls you down. Then separately, in relativity, space-time curves. Then separately, astronauts float. Then separately, gravity affects time. Those are presented as separate facts to memorize. The never explained like this version is that they are all the same idea seen from different angles. The scale reading is the same idea as the elevator experiment. The elevator experiment is the same idea as orbit. Orbit is the same idea as geodesics. Geodesics are the same idea as curved spacetime. Curved spacetime is the same idea as gravity affecting time. It's one story. Now, if you're waiting for the final question, the question that always lurks behind gravity, you're in good company. It's the one people ask with a slightly annoyed tone, as if the universe owes them an explanation. But why does mass curve spacetime? This is where Feynman's intellectual honesty matters. We can describe the relationship. We can write equations that connect energy and momentum to curvature. We can test those equations. We can use them to predict black holes, gravitational waves, the precession of Mercury's orbit, and on and on. But if by why you mean what is the mechanical medium, like gears or pressure that forces space-time to curve, then we're not done. Our current understanding is not a final explanation in that sense. General relativity is an extraordinarily successful theory, but it is not yet welded seamlessly to quantum mechanics. There are regimes inside black holes at the Big Bang where we expect the story to change. So the most honest ending is not a shrug. It's a celebration of what we do have and a clear boundary around what we don't. And now the most Feynman-friendly ending. We can predict gravity with absurd accuracy, but the universe still dares us to explain why this geometry exists at all. If you walk away with one new lens, let it be this. Whenever you feel weight, what you're feeling is not gravity reaching out and grabbing you. What you're feeling is the world refusing to let you fall in the simplest way nature allows. Gravity isn't just something that makes things drop. It's the name we give to the shape of the paths things take when nothing is touching them. And the next time you stand still and feel heavy, you can catch yourself in the act of doing something surprisingly non-trivial. You're not resting in the deepest sense. You're being pushed upward every second by the ground beneath you because, left alone, you would fall. And that's the version of gravity most teachers never actually say out loud.